There we go. Okay, does anyone have any questions to begin with?
Yeah, I do.
Go ahead, Charlotte.
Questions 65 and 66.
From the book?
Yeah, they're the same type of question.
Okay, so here's 65. Let's do 66 because I think I have that one written out and we can look at the question while I'm doing the problem. Okay, here we go. So, can you guys see 66 here?
Yeah.
Okay, so they're asking, how do you get to these products? What would X and Y be? I'm not sure what they're looking for in A. This could be one of those reactions where you have a sulfite react with an acid. Those are reactions that I'm not that familiar with. So let's take a look at that. I have a sneaking suspicion. Actually, that's not true, because that would be a gas forming reaction and that's not a gas. So about the only way I know that this can happen is that you have some sort of an acid base type of reaction like this. Okay, so this is an acid base reaction where this is the base and this is the acid. These two hydrogens would add on to NH3 and make NH4 plus. So this is in light of the Bronsted-Lowry type of acid and base. Where this is the acid, the proton donor. This is the base, the proton acceptor. So that's what I would do for A. And at first I was thinking this might be one of those gas forming reactions, but there's no gas here. So I think A is probably going to be the hardest of all of them. Let's take a look at B. So this is definitely a gas forming reaction because we have this CO2 gas. And I know that when you get CO2 gas and H2O, you want to start with a either a carbonate or a bicarbonate. So we want to start with CO3. And here it looks like we're going to have calcium here. And the question is, do I want to start with calcium carbonate or calcium bicarbonate? And I'm just going to try calcium carbonate to begin with. Now I know that this is going to be a solid because carbonates are not soluble in water unless combined with sodium, potassium, ammonium, or something like that. Now, to get the H2O and the CO2, you have to react this with an acid. And the acid that makes the most sense is HCl because of that Cl there. Okay, so we have our acid, we have our carbonate, and we're going to get CO2 and H2O and calcium chloride. This may not be the same order as given above, but it is the same reaction. So any questions about B? How about C? looks to me like an ionic solid. And so I think that this is going to be a precipitation reaction. So for precipitation reaction, all I'm going to do is I'm going to take that and combine it with chlorine, and that and combine it with silver. This one, I know that if I start with barium chloride, I need 2 chlorides. And here, if I have a silver and a nitrate, I'm going to need 1 silver and 1 nitrate. And I'm going to make these 2 products. So after I write this down, I'm going to give you a chance to check it out. So again, what I did is I noticed this was a precipitation reaction. So naturally with a precipitation reaction, you're going to take the cation of the solid and make it with the anion of the other stuff that's dissolved, and vice versa. And of course, when you write the formulas of these compounds, they're going to be neutral. Now we have to balance it. And you can see we have 2 chlorines here and 1 here. So we're going to have to put a 2 here. Now we have 2 silvers here and 1 here. So we're going to put a 2 here. And now we have 2 nitrates here and 2 here. We're good to go. Any questions about letter C? Oh, I got to move my hand down. Are we good to go?
Yeah.
Okay. And then D, I'm going to move everything up. Now this one looks like an acid-base type of reaction again. And so I'm going to start off with this HClO4 and mix it with water.
Mhm.
So our choices are pretty much acid-base, redox, gas forming, or precipitation. And if you look at the reactions above, can you see why I would go with precipitation for C and
Yeah.
gas forming for B? And these last 2, if it's not gas forming and it's not redox, my choices are going to be if it's not precipitation or gas forming, then it's got to be acid base or redox. Now, why would I not choose redox for either of these? And the answer is, I don't see a pure element in the formula, so I don't think it's redox. So that's why I went with acid base. So that's kind of the reasoning I applied here.
For D, though,
What's that?
for letter D,
Yeah.
for an acid base, wouldn't we have a water and a salt?
That's when you're looking at the Arrhenius acid base type of thing. Okay. When you look at a Bronsted-Lowry, you don't need to have water as part of your product. So
Okay.
here, do you see how we don't have water as part of our product? This is a base and this is an acid.
Mhm.
And here, this is a base and this is an acid. Water is a base in this particular case. What you have to have for an acid base is one of 2 things. One would be water and salt as products. But the other definition could simply be a proton donor and acceptor. So we have 2 definitions we have to look for an acid base. And how do you know you have a proton donor? And the answer is, if you see something on the left, well, actually, I'm going to go with proton acceptor. If you see something on the left that has fewer protons than the same formula on the right, then that's a proton acceptor. So this NH3 is a proton acceptor. This H2O is a proton acceptor. So for these acid-base reactions, you have to look for 2 possibilities. the Arrhenius, which would be a water and a salt, and the Bronsted-Lowry, which would be a proton donor and acceptor. Okay.
Okay.
So yeah, it's not, there are things that you peel off. So redox is easy to tell. Precipitation is pretty easy to tell. Gas forming is easy to tell. Redox, you got an element, pure element. Precipitation, you have a ionic solid. Gas forming, you have a gas. And then acid base, we got water and a salt, or proton donor and a proton acceptor. And of course, they will be different things. Okay, so that would be 66. Okay, other questions? All right, Charlotte, what are you eating?
Yogurt.
Is it good?
That's okay.
Okay, well, if you don't have any other questions, then we're going to start doing some problems from the back of the book. I believe we left off, let me see if I can find it. I think we got into the 40s. I know we did 42. We did that one. We did that one. I don't think we did 50. So take a look at 50 and tell me whether or not this looks like a problem we've done. Okay, so since I'm not getting a response, I'm going to assume we haven't done this one.
No, I don't think we have.
Okay, so we have the mineral rhodochrosite is manganese 2 carbonate. Write an overall balanced reaction for the reaction of the mineral with hydrochloric acid and name the products. So we have to know that manganese is Mn 2 plus. And I know it's 2 plus because it says so right here. The carbonate we know is CO3 2 minus. So the formula for this manganese 2 carbonate is going to be MnCO3. And we know it's a solid because carbonates are not soluble. Now this is going to be react with hydrochloric acid. And whenever they say hydrochloric acid, we're just going to assume that it's a aqueous solution. Okay, so here we have a carbonate and here we have HCl. So this is going to be a gas forming reaction. Whenever you have a gas forming reaction with a carbonate, you're going to rely on this being one of the things that you make. However, this thing does not last and it becomes H2O and CO2. The reason I write this out is because you can see what looks like carbonate here, whereas over here, it's harder to see the carbonate. It's the CO2. The carbonate is turned into carbon dioxide. So here, to make this, we need 1 carbonate and 2 hydrogens. And can you see that we have the 1 carbonate, but only 1 hydrogen? So our fix is to put a 2 here so that we have 2 hydrogens. So because of that, we should get H2O. That's a liquid, and CO2, that's a gas. And we have a salt here. The salt are the remaining ions that don't really react. The chlorines don't react. So we have these chlorides, 2 of them. And over here we have the manganese. And here you can see that that's a match made in heaven. 1 of these with a +2 charge, 2 of these with a -1 charge. And we also know that since this is a solid mixed with something in water, that there's going to be water at the end of it all. And we know that chlorides are soluble unless they're combined with certain things. So like silver or lead. So here we know this will be aqueous, and this would be your balanced reaction. Now name the products. Let's name them based on what we've learned for the standard way of naming things. So this would be dihydrogen monoxide. This would be carbon dioxide. And this would be manganese 2 chloride. So I guess I need to put my little square around that too, because it does say to name them. Are we good to go on that one?
Yeah.
Okay. Okay, write an overall balanced equation for the reaction of a sodium sulfite with acetic acid. Now, this I'm pretty sure is one of those gas forming reactions. And frankly, I have to look it up because this is not one. Oh, and you see the mistake I've made?
That was simply
3 and 4. This is sulfite. And I'm not sure what the gas is that forms here. So I need to look it up. So has anyone memorized those reactions with sulfites? Because maybe you could save us and just tell us. No one, huh?
on page 147.
Okay, so here we have a metal sulfite plus an acid is going to give you SO2. Whoops, that's not aqueous, that's a gas. Okay, and you're going to get H2O. And I'm willing to bet that we can figure out the rest of this. So the SO2 comes from the SO3, right? The H2O comes from 2 hydrogens here, because I know that these hydrogens here do not react. So that's why I put a 2 here for those 2 hydrogens. And if we look at what hasn't reacted, we have 2 sodiums and we have 2 acetates. Whoops. And you might be wondering, well, what about this other oxygen? That other oxygen ends up here as part of water. So how do we write a formula for what remains? And that is like this. How do I know it's aqueous? Because it has sodium. How many of these do I have?
2.
2. So from now on, you're going to remember, hey, if I have a sulfite with an acid, I get sulfur dioxide and H2O. Now we're supposed to name the products. What do we call this first one? Sulfur dioxide. What do we call the second one? Dihydrogen monoxide. And what do we call this last one? Sodium acetate. Now, for any of these, do you see how the coefficient does not come into naming it? We name the substance without regard to the coefficient. Are we good to go on that one? Okay. Determine the oxidation number of each element in the following compound. I think we did a little bit of this, so let's take a look at these one by one. And what I'm going to do is I'm going to put these over here like this, and we're going to look at A, PF6 minus. So the first thing we do when we assign these things is we look for neutral elements, because if they have neutral elements, the oxidation number is 0. I'm talking about neutral pure elements, but there are none of them here. Next thing I'm going to do is I'm going to look for monoatomic ions. And here, when I look at this, there are no monoatomic ions, so I don't use that rule. And then I use the next rule, which is fluorine in compounds is a -1, hydrogen is a +1, oxygen is a -2, and chlorine is a -1 in that order. So here I have a fluorine compound. So these are going to be -1 each, because you do it in that order, FHOCl, which if you sound it out, sounds like a bad word, okay? So if this fluorine is a -1, the first rule is that the oxidation numbers have to add up to the charge. So what does the charge on phosphorus have to be so that all of these oxidation numbers add up to -1? Well, if I have 6 of these at -1, that's a -6 total. To get a -1 total, the phosphorus has to be a +5. Now, when you're writing out oxidation numbers, you do want to write pluses and minuses. Don't leave the plus off. Any questions about A? So B, there is no fluorine. There are hydrogens. So the hydrogens are going to be +1. There are oxygens. The oxygens are going to be -2. And let's see if we can figure out what this arsenic is going to be. Well, you've got 2 hydrogens at +1. There they are. You've got the arsenic, which you're trying to figure out. You've got 4 oxygens at -2. And when you add these all up, what do they have to equal? We have a charge of -1. So that has to equal -1. All these -2s are -8. -8 and +2 is -6. So we have arsenic -6 is -1. And then arsenic is equal to +5. So we've got +1, -2, and +5. I'm going to pause the recording for a second. Not going to pause it. Hang on. Oh, thank goodness it went off. I got to get rid of that landline. Okay, for C, we know that oxygen is a -2. So what does uranium have to be so that we overall have a +2 charge? And the answer is it's got to be +4. Now, remember, these are not charges on the atoms. They are oxidation numbers, because all of these are atoms that are pretty much covalently bonded together. So D, the oxygens are -2, so the nitrogen is +5. You can see I'm speeding up a little bit. E, we have the oxygens are -2. The chlorines are -1. So we've got -3 due to the chlorines, -2 due to the oxygen, for a total of -5. So the phosphorus has to be +5. And F, the oxygens are -2. So the xenon has to be +6 because we have 4 oxygens at -8. Xenon at +6 would add up to a -2. Are we good to go on oxidation numbers? Okay. So here we're actually asked to do something with those oxidation numbers. Which two of the following are oxidation reduction reactions? Explain your answer and classify the remaining reaction. So here, if we take a look at these, which are the oxidation reactions? So redox reactions. And the answer is B and C. The explanation, both involve a pure neutral element with an oxidation number of 0. That same element has an oxidation number of -2 on the other side of the equation, right? See, here's oxygen, 0. Second equation, B, oxygen with the 0. On the other side of the equation, that oxygen's a -2. Here we have oxygen with a 0. On the other side of the equation, it's a -2. On the other side of the equation, the oxidation number changes. And that's all you really need. And if there's a change in your oxidation number, it's a redox reaction. So this would be a really excellent explanation for why that's a redox. So that leaves us with this one above. And I think it's pretty clear that A is a precipitation reaction. So what's our explanation for that one? 2 aqueous ionic solutions produce a ionic solid. So can you read that on the bottom there? Is that all right?
Yeah.
So that's how I would classify each of these. Any questions there? Are we good to go?
Yeah.
Okay. Going once, going twice, gone. In the following reactions, decide which reactant is oxidized, which is reduced, designate the oxidizing agent and the reducing agent. So let's do this for A. I'm going to cover up B. So for A, here are the oxidation numbers. Oxygen is -2 each for a total of -14. Now, to get a -2 charge, I need the chromiums to come up with a +12. So that means a +6 each. Okay, my tins are +2, and that's each, of course. Because the rule is if you have a monoatomic ion, the oxidation number is equal to the charge. Here, the oxygens or the hydrogens are +1 each, and the oxygens -2, and that comes up with that +1. The chromiums, these are +3 each. The tins, these are +4 each. Here, we've got a +1 each and a -2. So let's see if any oxidation numbers changed for any of these. Can you see how chromium at a +6 changed to a +3? Now the oxidation number has decreased, and I use an arrow for decrease. When you go from $6 to $3, that's a decrease. Can you see oxygen's a -2 here, and a -2 here, and a -2 here? So the oxidation number on oxygen has not changed. On tin, it's gone from a +2 to a +4, which is an increase. Okay. Here, these hydrogens have gone from a +1 to a +1, so they have not changed. And this oxygen was a -2, and over here it's still a -2, so it hasn't changed. So we're supposed to decide what is what. And the reason I do the arrows up and arrows down is because it really helps me out. So arrow down means that this chromium is reduced. So that's the one that was reduced, the chromium there. Now, when it's reduced, I like to say that it's been rigged as oil rig. The G in rig means it gains electrons. And it also means it's the oxidizing agent. So whatever happens to that element, it is the opposite type of agent. So if the oxidation number increases, it's oxidized, which means oil from oil rig, and the L means loses electrons. And notice the word loses, 1 O. That's loses. Don't write loses. Loses electrons, and it's the reducing agent. So on an exam, I normally ask for what reactant is oxidized, which is reduced, which one gains electrons, which one loses electrons, and which one's the reducing agent and which one's the oxidizing agent. And for the gain and lose, oil rig makes all the difference in the world. So this is a great explanation for what's happened if you have the equation written out ahead of time. Any questions there? Or are we good to go?
Yeah.
Okay, let's try B. So the oxidation number, this one, it's ionic. And I know that iron and sulfur, the sulfur's got to be a -2, so the iron is a +2. Okay, so this is ionic because it's a metal and a non-metal. So I've got a +2 and a -2. I know oxygens are -2. And so this nitrogen has to be a +5 for this to work out to be a -1. And here I've got a +1 and a -2. And you can see I've given up on the each. Don't put the totals down here, just put the oxidation number on the particular atom. What's nice about these compounds is if you find the oxidation number for one atom of an element, it's the oxidation number for the other ones also. So here, -2, -2, -2, +1. I'm going for the low-hanging fruit. +3, that's an easy one. This nitrogen clearly has to be a +2. And this sulfur has to be, well, I know that with the 4 of these, that's -8 total. So if sulfur is 8, it will be 0. So I got to make the sulfur a +6 so that it ends up being a -2 overall. Okay, so start off with iron. Does iron change?
Yeah.
Yeah, it goes from a +2 to a +3. So I'm going to draw a little arrow like that, and that's an increase, right? Does sulfur change? Here's a -2 and here's a +6. Hot diggity darn, it sure does change. And go from -2 to +6 is definitely an increase, right? How about nitrogen? Does it change? Yep. It goes down. How about oxygen? Does it change? Well, -2, -2, -2, -2. Oxygen doesn't change. How about hydrogen? +1. It doesn't change. So it turns out that we have one thing going down. Does down mean reduced or oxidized?
Reduced.
Reduced. Does reduced mean oiled or rigged?
Rig.
Rig, because of the R. Does rig mean gain or lose?
Gain.
Gain. And what type of agent?
Oxidizing.
Oxidizing. Okay, now what happened to the iron? Up means it's oxidized. Oil loses electrons and it's the reducing agent. But also that happens for sulfur. Sulfur is also oxidized, loses electrons, and it's the reducing agent. So overall, this FeS is the reducing agent because of both elements in there, not because of one.
So how would we answer this question with there being two reducing agents?
We just did.
So FES.
This tells you what's going on, right?
Okay.
Especially
wouldn't
if
need-
you got to have the equation written out though above.
So we wouldn't need to do anything differently.
No,
if
because
there
you
are
know,
two.
this looks like it's iron, right?
Mhm.
This looks like it's sulfur, and this looks like it's nitrogen. So this is pretty well laid out where you can, as long as you're writing the numbers underneath the elements, it should be fine. Okay. Okay, balance the following. Classify them. So if I take a look at A, I'm thinking right away it's a precipitation. Do you see why? Here's 1K. Here's 2 Ks. Here's 1, so I'm going to put a 2 there. One copper, 1 copper. So this looks to me like it's balanced now with a 2 here in front of there. B looks like it's also going to be a precipitation reaction. 1 lead, 2 nitrates, 1 nitrate. So I'm going to put a 2 in front of there. And then I'll have 2 hydrogens and 1 hydrogen, so I'll put a 2 in front of there. So that 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 and precipitation. C looks to me like it's a gas forming reaction because of the CO2. So I know to make this right here, I have to have 2 hydrogens and 1 carbonate. Here's my carbonate. There's only 1 hydrogen, so I need 2 of those. So I'm going to write MgCO3 solid plus HCl aqueous, and I need 2 of those to get 2 hydrogens. And then I'm going to have MgCl2 then I'm going to have H2O, and then CO2 gas. And that's going to be a gas forming. Now, normally on a test, you don't want to do this where you say this is a precipitation here and this one's a precipitation here. So maybe you do this. So it's more, it conforms more to the same type of answer or presentation. Okay. All right. Classify each of the following as precipitation, acid, base, or gas forming. Show states for each product and balance. Finally, write the net ionic. So let's take a look at this. First of all, I know this can't be a precipitation reaction because nitrates are soluble. Secondly, I don't think it's a redox because there's no pure element. Thirdly, I don't think it's a gas forming reaction because I don't see one of the gases I would expect to see here, like sulfur dioxide or carbon dioxide. So that only leaves an acid base, and indeed I have an acid and a base. So how do we balance acid base reactions? We make sure that we have the same number of hydrogens as hydroxides. Here we have 3 hydroxides and only 1 hydrogen. So I'm going to put a coefficient of 3 in front of HNO3. So I have 3 hydrogens. Now, when you have 3 hydrogens, you're going to make 3 waters. And here, let's see if this balances out. Now, water has a state of L. This is going to be aqueous because nitrates are soluble. And I believe this is balanced, and we're going to call this an acid base. So this is a fine abbreviation for an acid-base reaction. I'm not sure what else AB could stand for. Okay, now for the net ionic, remember, everything above that is a solid, liquid, or gas comes right down. So we're looking at the net. Anything that is a solid, liquid, or gas comes right down. Now, for the other things, you have to remember a few things. For instance, nitric acid is a strong acid. So when you put this into water, what you actually have are dissolved H pluses and dissolved nitrates. So that's what HNO3 actually gives you. And it gives you 3 of these and 3 of these. Since this is aqueous, it gives you an iron 3 and 3 nitrates. Okay, so after I brought down all of the solids, liquids, and gases, I then look at the aqueous things and I ask, what are the ions there? Now, take a look at these ions. Do you see how we have 3 nitrates here and 3 nitrates here? These are called spectator ions because they start off and end off the exact same way. And spectator ions do not belong in the net. So these don't belong in the net, but these 3 hydrogens do. And this one iron does. Now, if we've done this right, we will have the same atoms on both sides of the equation and the same charge total on both sides of the equation. So here we see we have one iron, one iron. We have three oxygens, three oxygens. We have three hydrogens and three hydrogens for 6. And here we have 6 hydrogens. Over here on the left, we have 0 charge, +1 for 3 of these. So +3 total. On this side, we have +3 and 0. So +3. So the charges match on both sides, as well as the number of atoms on each side of each type. So any questions about A? So I want you to give B a shot. See if you can figure out what type of reaction, write the net ionic, and so forth and so on. So give me a little thumbs up when you're done with B. Okay, are we good to go? Let's take a look here at where I would start. I'd start with the states of these things. CO2 I know is a gas. H2O I know is a liquid. So I'd start there. And I would surmise that since we start off with this being aqueous, and since this has a nitrate, it's also aqueous. To balance it, one iron, one carbon, one carbon. I know that to make this CO2 and H2O, I need 2 hydrogens. I only have 1 here, so I'm going to put a 2 there. So I've got my 2 hydrogens and my 2 hydrogens. I've got 3 oxygens and 6 more here for 9 oxygens total. Here I've got 1 oxygen and 2 for 3 total. And here I've got 3 times 2 is 6, plus my 3 over here means 9 total. So the number of oxygens match, and the nitrogens, I have 2 of them and 2 of them here. So everything is balanced. Okay, net ionic. What do we bring down? We bring down this because it's a solid. We bring down the CO2 because it's a gas. And we bring down the H2O because it's a liquid. Now, what are the ions here? Well, you've got 2 hydrogens and you've got 2 nitrates, and they're both aqueous, and these are both aqueous. Here you've got 1 iron. and you've got two nitrates. You can see that the two nitrates and the two nitrates are exactly the same. They're both aqueous, so these are spectators. I'm going to put SPECT, specs. And so I need to include these two hydrogens in my net and this one iron in my net. And if we have done this right, we will have the same atoms on each side and the same total charge on each side. One iron, one carbon, three oxygens, 1, 2, 3 oxygens, two hydrogens, 2 hydrogens. On the left, since I have two H pluses, I have a +2 charge on the left. And on the right, I've got a +2, a 0, and a 0, so I have a +2 on the right. So the charges add up, and so do the atoms. Any questions about B? We good to go? Okay. 66 we already did. 68, refer to the book, not going to do that. Well, we're going through the problems really quick now. 70. Give the formula for each of the following compounds. So, a soluble compound containing the acetate ion. Well, you can't go wrong with putting a sodium with the acetate ion because you know that sodium compounds are soluble as well as acetate compounds. So don't fiddle around, just do something like that. Or that. Either of these are fine. Even this would work. These three answers that I've just shown you are all the same thing. Any questions about A? B, an insoluble sulfide. So sulfides are generally not soluble unless you combine them with like sodium sulfide, potassium sulfide, or ammonium sulfide. So don't put them with those. Put them with something else. Now, since this has a -2 charge, I'd like to put it with something that has a +2 charge. So I'm thinking magnesium. Any questions there on that one? You can put a whole lot of different things there. C, a soluble hydroxide. So hydroxide is a -1. So naturally, I'm going to pair that up with sodium to make it soluble. An insoluble chloride. So chlorides are soluble unless you mix them with like lead-2 or silver. Silver is the go-to here. E, a strong Bronsted base, NaOH. Okay. Name 2 anions that combine with aluminum ion to produce water-soluble compounds. So we got to think about anions that are always soluble. And the 2 that come to mind are the acetate and the nitrate. So one of the formulas would be Al CH3COO3, and the other would be AlNO3. Are there other soluble anions? Sure, like a chlorate and perchlorate are pretty soluble, but these are the 2 you really should memorize as being always soluble anions. So these are the go-tos. Are we good to go on 72?
Mm.
74. Identify and name the water insoluble product in each reaction and write the equation. So for water insoluble product, I'm looking for an ionic compound that does not dissolve. So I think it's pretty obvious that for A, it's the copper 2 sulfide that is insoluble. So identify and name the water insoluble product and write out the ionic equation. So I'm going to go ahead and write out the total reaction. Now this is probably going to be aqueous. Okay. So for the net ionic, what are we going to bring down? We're going to bring the copper and the sulfur. Now, when we take a look at this, this turns out to be an acid, but it's not a very good acid. Now, how do I know it's not a very good acid? Well, because these two are very similar. Sulfur is in group 6A and oxygen's in 6A. What do you think of H2O as being an acid? Is it a good acid or a bad acid?
Bad.
If it's a good acid, you would throw it on someone and they would like melt. Does water do that to people? No, just makes you wet. So since this is a weak acid, you're going to say that the formula for that is H2S. Now this is aqueous, so you've got copper 2 plus aqueous and Cl minus aqueous, and there's two of them. So this is what we have for this guy right here. And for this guy, we've already brought it down. This is a strong acid, so you've got 2 H pluses and 2 chlorides. So can you see that these are identical on either side of the arrow? What do we call those things that are identical on either side of the arrow? Remember, this is like a sporting game, sporting match, right?
Mhm.
And these guys aren't doing anything. They're just watching. What do you call them?
Spectators.
Spectator ions. And spectator ions do not belong in the net. So I want my 2 hydrogens in the net. And here I want my H2S in the net. And I want my copper. So that would be your answer for A. Oh, and we're supposed to name that water insoluble copper 2 sulfide. So technically, this is what we're supposed to write out.
So we're not separating H2S because you said it's a weak base or weak acid.
Weak acid. Weak acids you don't separate out. Strong acids you do. Okay, let's look at B. So for B, I'm going to have calcium chloride, aqueous, plus potassium carbonate, aqueous. And I'm going to have 2 KCl, aqueous. And I'm going to call it aqueous because of the potassium ions. And then I'm also going to put calcium carbonate as a solid because I know that carbonates are not soluble in general unless you combine them with 1A ions or ammonium ion. This looks balanced. So we have a calcium 2 plus aqueous plus 2 chlorides aqueous plus 2 potassiums aqueous plus a carbonate that's aqueous. And then we have 2 potassiums that are aqueous plus 2 chlorides that are aqueous plus calcium carbonate, which is a solid. So I'm going to get rid of the potassiums because they're identical on both sides of the equation. I'm going to get rid of the chlorides since they're on both sides of the equation. So my net has calcium with a +2 charge, carbonate with a -2 charge, and calcium carbonate solid. And that's my net. What do we call this? We call this calcium carbonate. We good to go? Okay. C. So I'm going to let you work on C. When you're done with C, give me a thumbs up and then I'll show you my answer. I'll also show you how I get to my answer.